Welcome to lesson 4 from chapter 3, Pure Mathematics Year 2, and today we're going to look at inverse functions, and we're going to use a graphical method to find out exactly what inverse functions are and how they behave and some of their key properties. So there's quite a few key words today. We're going to be looking at domain and range. We're going to look at composition again, the idea of a composite function, what an inverse is, and you're also going to see reflections as well. So the idea of transformations is going to creep in as well. So please pause the video, try the beg your pardon, there's only 3 warm-up questions today, and I'll go through them momentarily. Okay, let's have a look at question 1. All right, so a bit of revision from the previous lesson on compositions of functions. We have to find f2 of x and g2 of x, or f squared and g squared. If you remember, another way of writing f2 would be, so I'll call this part 1. I'm not stipulated any particular parts of this question, so 1 and 2, we'll do it like that. So for part 1, if we say f2 of x, as you'll recall, what we mean is ff of x. So we compose f with itself like that. And that means that we take the function f and our input is also going to be f, so f of x. So we input f of x into f and we see what we get out of it. Now, if we do that, of course, this means that the input f of x, if we just check what this is actually equal to, so f of x here, well, looking at our notation, it's the other type of notation, but we know that that just means f of x, and if you're not comfortable with that, just make a note of that. This is just f of x is equal to 2x plus 1, and similarly below g of x is equal to x subtract 1 over 2. All right. Now, if we input f into itself, the input is, of course, going to be 2x plus 1, like that. Okay. And so that means that anywhere I see an x in my function f, I just replace it with 2x plus 1. So it only occurs here. So my composition, my first step when I've actually composed the two is to actually write 2 lots of 2x plus 1 like that, and then add 1. So that's like a nested function. And this is only defined for x is greater than or equal to 0, but it's just the actual composition we're interested in. So this is going to give us 4x plus 2 plus 1, which is going to equal 4x plus 3. And you'll recall as well from what we said in the previous lesson, if you're taking some function f from a domain, as we are doing, to some range, okay, so everything in here is called f of x, given that the input will be called x. Then if we compose it with itself, this is obviously going to give us another branch of this, so f would be applied to itself again, and everything over here on the right would be f of x. But you'll notice, of course, that if I take the overall function ff, it shares the domain with the original function, doesn't it? So ff has a domain of x, this set here, which we talked about earlier, so it's the same domain for ff, so I can just write that down as well, just to be complete. So this is going to be defined for x is greater than or equal to 0 as well. Okay, and we do the same thing for g. So we compose g with itself, same arguments, of course. So g, nothing to do with horse racing or anything like that. So g squared of x is equal to g of x, which we know is also g of x like that. So we substitute whatever g is into itself. So the input, wherever I see g of x, that's going to be x subtract 1 over 2, like that. I'm going to subtract that, or sorry, substitute that into itself. Okay, so that's my input here. Okay, so I've got to make sure that that input corresponds with the input here and here. So I'm going to have the following. So this is going to give me, let's get my pen right. So this is going to give me x subtract 1 over 2. Now I'm going to have to subtract 1 from that and then divide the whole thing by 2. So subtract 1 and divide the whole thing by 2. So this can sometimes happen. So we've got a situation where we've got a fraction within a fraction, but it's not a big deal. We can clear the fraction simply by multiplying top and bottom. So if I multiply the whole of this numerator by 2, that will clear the fraction. But I've got to also make sure I do the same thing to the denominator. So if I do that, so this whole thing is just going to be x subtract 1 to clear the fraction. And we did this in a previous lesson, didn't we? Okay, and multiply the negative 1 by 2, so that's going to be subtract 2 all over 4. So it immediately looks a lot better. Okay, and then just to conclude, this is going to be x subtract 3 all over 4. And then, of course, the domain is going to be exactly the same from the argument I talked about previously. It's the same domain as g, so only defined for x is greater than or equal to 1. Real numbers as well. So that's question 1 done. Now then, for question 2a, because this is quite a large graph we're going to be drawing, I'll do 2a separately, then we'll scroll down and do parts b and c. So if we look at 2a, it says complete the table of values for f and g. So I haven't stated it explicitly. I mean the same f and g defining question 1. All right, so we're basically just substituting in the values. Well, if we look at the function f, if it's 2x plus 1, so I'll just make a note of that. F is just 2x plus 1. So straight away, we know the y-intercept is, of course, 1, so that's going to go in there. And then as the numbers increase by 1, we're going to be adding 2 each time. But just watch out because there is a jump at x equals 4. So let's just fill these in. So we've got 2 times 1 plus 1, which is 3. Add 2 more to that, so that's going to be 5. Add 2 more to that, so that's going to be 7. Okay, now we've got a jump, so we've got 9, and then it would be 11, but we're not interested in that because it's grayed out. All right, so that looks pretty good. Now, for g, we have to subtract 1 and divide by 2. Okay, and we've only chosen the ones that will give us even values, so we don't have awkward numbers to plot here. So x subtract 1, so 1 subtract 1 divided by 2, that's of course going to be 0. Okay, so 1 subtract 1 is 0, divided by 2 is 0. 3 subtract 1 is 2, divided by 2 is 1. 5 subtract 1 is 4, divided by 2 is 2. And 7 subtract 1 is 6, divided by 2 is 3. Okay, so we've filled in our table of values, and the next job is to plot these graphs on the axes and state the equation of the line of symmetry. So we'll do that next. Okay, so for part B, I've plotted the graphs on the axes for you to check. F of x is the orange line and g of x is the green line. And there's just some interesting things to pick out of this. You'll notice they have a clear symmetry about them, which we'll talk about in more detail in a minute. But also, if you notice the domains that I specified in question 1 for f, this is defined clearly for all x values greater than or equal to 0. You can see that from here. It starts at 0, 1, the first coordinate, and it's clearly defined. So we can actually state that on there and just verify that. So this is valid for x is greater than or equal to 0. And if you look at the function g here, this is only defined for x values greater than or equal to 1. As specified also in part 1. So that's something to just bear in mind. So the domains do actually match up, and you can see this symmetry. Hopefully, if you can draw the line of symmetry on here, that'd be really good. There's definite symmetry along these points here. If you count 2 squares across, 2 squares down, we can see that there is definite symmetry all the way down. Okay, that's just a particular point, of course. And here we have 3 squares across and 3 squares down. All right. So if we just plot that as a line, I'll just put some points on here. And I'll add that to the graph. So it looks like it's passing through the origin. And as all the scale is 1 to 1, this clearly has the equation y equals x. So the graphs are symmetrical about the line y equals x. Okay. Something else to bear in mind as well. We'll get onto this a bit more later on. If you look at the domains that I've just mentioned, x is greater than 0, and then look at the range of values for our function g here, you can see g is defined for all y values greater than or equal to 0 because it starts on the x-axis. So they seem to have a swap. So there seems to be like a relationship between the domain of f and the range of g. And similarly, if we look at the domain of g here, x is greater than or equal to 1, you'll notice that the y values for our function f are only defined for y is greater than or equal to 1. So it could be a coincidence, or maybe there's something in that. So let's move on. So we've got the equation line with symmetry. We've answered the question. So what we're asked to do in question 3 is to find the composite functions fg and gf. Right. So I'll just write them out again. I'm just going to use the space above here so we don't have to scroll down. So remember, f of x is, of course, 2x plus 1, where x is greater than or equal to 0, and g of x is x subtract 1 over 2 for x being greater than or equal to 1. Now, let's find the compositions. So let's do f of g, fg first. I'll call this one 1, this one 2. So for 1, we have to put g into f. So it's going to be f of g of x, like that, which means that my input into f is going to be whatever the function g is. So let's just check. So this g of x here, well, it's x subtract 1 over 2. Okay, so that's going to be my input. So let's just write that in. So that's x subtract 1 over 2. We'll close the bracket like that. And that means that I've got to write that as my input for f. Now, my input for f, see, is x here, so I replace x with x subtract 1 over 2 everywhere I see it. So this is going to be 2 lots of x subtract 1 over 2. Okay, we'll close that. And then I've got to add 1. So straight away, the 2's will cancel, so that's good news. So we've got this nice cancellation here, so they simplify to 1. So we're left with simply x subtract 1 plus 1, which of course is just x, isn't it? Now that's quite interesting because you remember we've talked about e and natural log before. If you do the composition e to the natural log of x, we also get x back, don't we? Because they're inverse functions. So the input is undisturbed because e and natural log undo each other. We've got the same thing here. Notice we've got x back when we compose f and g together. But you'll remember that this could be a coincidence. I don't know. But you'll remember that also, if we do the composition the other way around, if I do the natural log of e to the x, so where e is the function that goes first, is put inside as an input into the natural log, the x comes down if we use the laws of log. So that's going to be x log e, and we know that the log of e is just 1. So we get x again. So it works both ways because they're inverse functions. It doesn't matter which way you compose them, the input remains undisturbed. So we might have something going on here. So let's have a look at part 2. We're going to compose f and g the opposite way around. So we're going to do gf this time. So gf of x is going to be g of f of x. And notice I'm not cutting any corners here with this. I'm writing all the steps out carefully because I don't want to make a mistake. So this is g of, and my f input is, in this instance, so it's f is 2x plus 1. So that's my new input. So let's put that in. 2x plus 1. So wherever I see an x in the function g, I have to replace it with 2x plus 1. Well, let's have a look at my function g first of all. My x input there occurs in the numerator, so it's the input subtract 1. So I'll put my input in first. So it's the input subtract 1, so it's 2x plus 1 subtract 1, and then divide everything by 2. Okay, well, the 1s will cancel, so plus 1 minus 1 cancels. So that's going to give us 2x over 2, which of course is x. So we seem to have verified that. Now, so this appears that we have inverse functions f and g, and we've got lots of properties on show. So let's explore this and make it more formal as we proceed through this lesson. All right, so as an introduction to inverse functions, we've already seen, well, one example through the warm-up, but what you can do now is you've got an opportunity to write down some pairs of functions that will form a composition that will leave the input unchanged. So algebraically speaking, we need 2 functions so that if you have 2 functions f and g, as we can see here, the output is just the original input. So what I'd like you to do is pause the video and try and think of some examples whereby you have 2 functions, and when you compose them together, the input remains unchanged. All right. So there's lots and lots of different ideas here. You could use the one from the warm-up, as we saw. If you have 2x plus 1, and if you have x subtract 1 over 2, just ignoring the ranges and domains, that they were of course composed to give you just x. Another one I mentioned as well, if you have e to the x and the natural log of x, and you can have those swap round as well. They both compose to give just x. Lots of different examples. So another one could be x squared and the square root of x. Okay, now that one, you have to be careful, of course, with your input there, because if you're taking the square root, the x would have to be positive. And there's all other kinds. So you can play around with that to your heart's content, really. So there's 3 examples that I've just written on the board. You can come up with as many as you like. So moving on to the idea of what inverse functions actually are. So I'll just clear all this. we can build up a picture using a function machine. Okay, now what an inverse function does is it literally inverts the original function. So it undoes. So I'll just highlight this word inverse. The inverse of a function f reverses the operations performed by f. So it literally unpicks what f has done and returns you back to your starting point. Now, this is quite key. So it says here, an inverse function will take the elements in the range, okay? So not the domain, elements in the range from your original function f and map them back to elements in the domain. So we're gonna see what this actually means. Now, if we go back to the example from the warm-up, so we're going to look at f of x equals 2x plus 1 here with the specific domain x is greater than or equal to 0. Well, how does this behave? So the first box here, this is going to be the domain of my function f. So I'll shade this in yellow. I'm going to try and stick to yellow for domain and green for range. So we take an element from the domain, so some element x, okay, which is specifically greater than 0. And what are the operations that we are performing? Well, if we're applying f to this function, so f being 2x plus 1, the first thing I need to do is to multiply my element by 2, and then I need to add 1. So this is simply a function machine, isn't it? And my output, of course, is going to be 2x plus 1. And I'm now in the range of f. Okay, so this is the range. And if you take any positive x input or 0 and apply that, you'll end up in the range. So the other thing we can also do is just make a note of what we're talking about here. So this is the domain of f. Okay, and over here, this is the range of f. All right, and the two operations combined give you the function f, don't they? So f of x is equal to 2x plus 1. Okay. Now then, what do we do now? So we can now, now we're at the range. So we've gone on a journey. We've gone from x, we've doubled it, we've added 1, we're now at 2x plus 1. If we go backwards, we're going to take elements from this range and we're going to send them backwards, back to the domain. Now, in order to do that, we need to undo all these operations. So what I'm going to do, I'm going to take my input now. Again, I'm going to call it x, okay, although technically it is y, and I'll do it in red. And this is now the domain of the inverse function, okay? Because I'm starting with the range. I've got to map this range back to the domain. So what do I have to do? Well, I simply have to remove 1 from my x value, from my domain of the inverse of f. Then I have to divide it by 2, and that will take me back to my domain. But this is going to be a different function, isn't it? This is going to be, let's have a look, x subtract 1 all over 2. All right, and this is now the range of the inverse of f. So we seem to have swapped the domains and ranges around when we perform the inverse. So let's put this together more succinctly in a table. Okay, so we don't know what this function's called here, but we'll call it just g for now, which is what we called it originally. So that's x subtract 1 over 2. Right. Now, so what we do now is we're going to put all the results together in a table. Now, the g of x which is the inverse function, okay, this thing here, you'll notice this is now represented by f to the -1 of x. So they're the same thing. And this is the notation for the inverse function. Okay, so this just simply means the inverse of f. So the notation is f to the -1. Okay, so let's fill in what these functions actually are. So this function was x subtract 1 over 2, okay, with an input of x, right? So we've got that. Now let's go back to the domains. So the domain of f, well, this was stated here, wasn't it? So the domain of f, I'm allowed any positive real number. So it's a real number, but the restriction is that it has to be greater than or equal to 0, according to this. And what was the range that we got out of it? Well, we plotted it on the graph in warm-up question 2. The range that we got was that you get a y value, but the y value would be greater than or equal to 1. Okay, and just to remind you, I'll just do a little sketch of that graph just to show you what I mean. So it was 2x plus 1. There's your x values, there's your y values. It looked like this. And your domain was all the positive x values like that. But because the y-intercept is, of course, at 1 here, okay, the y values that are defined are just going to be greater than or equal to 1. Okay, so that's where that came from. Now then, if we look at x subtract 1 over 2, go back to the sketch as well, and just from what we infer from previously, we're taking elements for the domain for the inverse function from the range of f, from here. Now, the range of f, as we've just discovered, is all y values greater than or equal to 1. So that means that that's the only choice I've got. I've got to choose values from this pool where the values are all greater than or equal to 1. So this is now what my domain is for my inverse function. Okay, so I can only choose values that are greater than or equal to 1. All right, because the domain and range have switched. And then if we look at the range for my inverse function, well, if I just sketch it from what we did earlier, again, so we had x values here, we had y values here, and it was symmetrical about y equals x, of course, wasn't it? It looked a bit like that. Okay, and it started at the point 1, 0. Well, the domain, as we know, was defined for x values greater than or equal to 1, as we can see here. But the y values, well, we can have anything that is greater than or equal to 0. So let's write that in. So my y values can be anything, but they have to be greater than or equal to 0. So that's really important. Now, I'm just going to get rid of that highlight for a second. Now, what's going on here? So we found the inverse function by simply undoing the mapping. Okay, so going back from the range to the domain and undoing the mapping using a function machine idea, basically. So subtract 1, then divide by 2 as inverse operations to these two operations here. And then, excuse me, with the domains and ranges, they just simply switch. So you'll notice that this domain here has become the range of my inverse function. And this range here has become the domain of my inverse function. Okay, so that's how functions and their inverses are related. So it's the domains and ranges are also related as well. So I hope that's given you quite a broad and slightly more in-depth analysis of what inverse functions actually are. So now we're going to look at cases where functions may or may not have inverses. So question is, do all functions have inverses? Or with a little asterisk after it. We'll talk about that in a minute. So I've given you a function with two different domains. Okay, so we're going to look at two different cases. So the function is f of x is x squared. And the first domain we're going to look at is this finite set here of integers from -2 up to 2 inclusive. And I've also done them as diagrams as domains and ranges. So we know what the mapping is. It's x squared. Okay, so the rule that takes us from the domain to range is x squared. So all we have to do is we just simply join these up. So 0 would be mapped to 0. Okay, 1 squared, of course, is 1. -1 squared is also 1. 2 squared is 4, and -2 squared is also 4. So that's the mapping. All right, so going this way in each case. So what kind of mapping is this? Okay, it's a function, definitely. Okay, but what kind of mapping is it? Well, we have more than one input going to one particular output. So this is what we will call a many to one. So this would be the many, because we have 2 inputs going to the same output, and then this is the 2 bit where the function is happening, and then the 1 particular output. All right, so 2 and -2 both go to the same output. All right, even if there were even in the case of 0, it's still a many to one function. Okay, there are allowed to be exceptions within it. So it's a many to one mapping. Right, now if we look at the second example, I've restricted the domain even further. So we're just taking 0, 1, and 2. Now if we do that mapping, and you can do this, or you can pause and do this yourself. So 0 to 0, 1 to 1, and 2 to 4. Same rule, of course. So each input, so one input goes to one output. So this is what we call a one-to-one mapping. Okay. So we've got 2 different mappings. By restricting the domain, we can create different types of mappings. So the question is, do both of these mappings lead to inverse functions? Well, the answer is no. And this is the reason. Because the domains and ranges switch, that's where the problem arises. So if we start with the one on the right-hand side, the inverse function of this with the inputs of 0, 1, 2, remember that the range becomes the domain, okay? So this is the range y equals f of x, but this is also the domain of y equals f to the -1 of x, wouldn't? Okay, I think that's consistent with what we've said already. And going backwards, so going backwards this way, this would mean that this is the range of y equals f to the -1 of x. Okay. Now that means that the mapping is still one-to-one, because we're going from the same one input here to the one output. Okay, it just means that I'm going backwards. Okay, so I'm switching the 2 words around. So the 2 ones that I've highlighted in orange would switch for my inverse function, and it'd still be a one-to-one mapping because it's the same word. Now, if we apply that same logic to our first example here, now this of course is the domain. So this set is the domain of y equals f to the -1 of x. I know it says the domain is just the x values, but it's the domain of that function. And over here, this is the range of y equals f to the -1 of x. Okay. Now, in this instance, if I'm going back, so I'm going from the range to the domain, there's no problem with 0 because 0 is one-to-one. But as I go down my list, if I look at 1 here, 1 would map to either +1 or -1. Okay, and similarly 4 would map to 2 or -2. So that means that in my inverse function, if I swap these two words around, so if I swap the word one and many around in my mapping, I would get a one-to-many mapping. Okay, so let's just write this out more formally. So for example 1, we have a many-to-one mapping. Okay, the many corresponds with the x inputs and the 1 corresponds with the outputs. In the inverse function, these switch around. So these would swap. Okay, so that means that my two words would just swap round. So the 1 would swap with the many. And I'm now going to get this. So many-to-one. So many-to-one will become 1-to-many. And we said previously, if you've had 1-to-many, you can't function. So this would be not a function. So this herein lies the problem. Not all functions have inverses. Okay, some functions exist as functions. There's no problem here. So if you have a function that is a many-to-one mapping, as we have here, so this is a many-to-one mapping. So it's x squared with some negative values and some positive values as your inputs. That's fine as it is as a function. There's nothing wrong with that. But if I want to try and find an inverse, the inverse of that would create a many-to-one mapping, which is not a function. So that means that the inverse does not exist. So this would have no inverse. However, by restricting the domain, there's no problem over here because this has an inverse. Because the inverse is also 1-to-1. So that leaves us with a condition, okay? The only way you can have a function that also has an inverse function is from this bottom point below here. The function has to be a 1-to-1. If it's not a 1-to-1 function, it can't have an inverse, okay, as we've just shown. And this is one of the many properties of functions and their inverses. So we'll just go through them briefly. F and f to the -1 are inverses of each other. Okay, so f is the inverse of f to the -1, and f to the -1 is the inverse of f. And as you've seen, if you compose them together, it doesn't matter which way you do it, they undo each other. So f undoes what f to the -1 does, and vice versa, and you're left with the input. We've also seen that the graphs of these two functions are reflections in the line y equals x, and that is because of the next 2 points. The domains and range switch, so the y values become the x values, so that's why you get the reflection in the line y equals x. So the domain of f is the range of f to the -1, and the range of f is the domain of f to the -1. So there's some really nice properties with functions and their inverses. So let's apply this information now to some examples. So our first worked example is quite a typical exam question on functions. We're given the function f of x, and it's a rational expression, and we're given this restricted domain as well. So x is only defined less than or equal to -5/2. So we're asked to find the inverse function, and we have to state its domain and range. Well, the erudite among you will already know that the domain and range are interchangeable for the inverse function. So we've already got the range staring at us if we know how to look for it, but more on that later on. So what we're going to do first of all is we need to have a really clear idea of what this function actually looks like, so we can actually find the range of the function. And we need the range of the function because that will switch over to become the domain of our inverse function. So let's have a closer look at this. Now, these rational functions can be quite tricky, but the first thing to look for is what's going on in the denominator. Now, in the denominator, we can see that if I substitute in x equals 3, we're going to get a singularity. So we have an asymptote, a vertical asymptote at x equals 3. And you can always find that by just imagining what would happen if that denominator was set equal to 0. Okay, so we have a vertical asymptote. I'll just make a note of this. So we have a vertical asymptote at x equals 3. Okay, but more, let's just do it a bit more thoroughly. So you just set x subtract 3 equal to 0. Whatever it is in the denominator, set it equal to 0 and then solve for x. Okay, so that's the equation of the vertical asymptote. Okay, so we've got that. So that's really good. We can also think what would happen horizontally. Is there a horizontal asymptote? Well, yes, there is. Horizontally, we just imagine what would happen if x suddenly got very big in the positive direction or very big in the negative direction. And you can do that using not a trick, but you can see what the horizontal asymptote would be by just doing away with the +5 and the -3. Simply because if you put in huge values of x, adding 5 to a massive number, such as like if you put x is 1 million in, adding 5 to 2 million is not going to do much. Neither is subtracting 3 from 1 million. Okay, you're essentially still got 1 million. So what would happen is as x approaches infinity, f of x would approach. Now, initially, it would approach 2x over x, like whatever x is. But because the +5 and the -3, you can just imagine they're not there, which would equal 2, wouldn't it? Okay, so essentially f(x) would tend towards 2. So our horizontal asymptote would occur where y equals 2. Okay, so that's good. So we've got 2 asymptotes, as we would expect, and as we've seen with previous rational functions. So we've got that. That's really good. Now, what we also need to consider is an x-intercept and a y-intercept. That will fix the curves in position because rational curves are always in the opposite quadrants. So we need to figure out what happens on the x-axis and also on the y-axis. So I'll do that in reverse order. So when, let's undo the highlighting function. So when x equals 0, well, if we just plug that in, f of 0, so just you can basically, you can't see my hand, but if you can just cover up this part of the function with your hand, what have you got left? We've got +5 over -3. So that you get -5 over 3. Oops, and I've just put that highlight function back on again. So that's the y-intercept. So the y-intercept is at coordinates, just highlight them separately, 0 here and -5 over 3. And that's pretty good. Now we could also find y-intercept. So I'll just do ditto mark. So when y is equal to 0, what happens? Well, the denominator can't possibly be 0. So we just have to consider when 2x plus 5 equals 0, the numerator. There's no way the denominator can be anything other than a non-zero amount. Otherwise, the whole equation breaks down. So you only have to consider the numerator. Plus, when you cross multiply, the denominator just becomes nothing anyway. Hope that's clear. So that implies that x is going to be negative 5 over 2. So we've now got our y-intercept. So y-intercept is going to have coordinates negative 5 over 2 and 0. So let's put all this together on a sketch. So we'll put on the axes first of all. So just think where our asymptotes are. We have one at x equals 3 and y equals 2. Put this somewhere in the middle. So something like that will be okay, I think. We'll just label the axes. So we've got x there, and we've got y here, and there's the origin. Put the vertical asymptote in first. So x equals 3, so let's put that in about there. And label it. So this is x equals 3. Okay, and we have a horizontal asymptote. I'll do it in the same color actually. At y equals 2. So something like that. So get those in first. I think that's a good idea to do that. Okay, so we've got the two asymptotes. The next thing we found was the y-intercept. So that was at negative 5 over 3. So that'll be down here somewhere. Okay, and the x-intercept is at negative 5 over 2. So I'll put that in there. So just want to keep the numbers out of the way. All right, and we can put the curve in now. So the curve is going to go through something like this. The asymptote is at x equals 3, so it's going to tend towards that point. Oh, I've missed it quite considerably. Let me try that again. So it's going to go through like that, tending towards y equals 2, and then there's going to be another curve here in the opposite quadrant. So we can label this graph now as y equals f of x. However, it's not quite y equals f of x, is it? What we have not considered at any point during this sketch is the domain. The domain is only valid for x values less than or equal to negative 5 over 2. So what that essentially means is that the top right branch is irrelevant. I also don't need to worry about this asymptote here either. Okay, the horizontal asymptote is useful, but I also don't need to worry about much of the bottom left-hand curve either, because x is only defined when it is less than or equal to minus 5 over 2. So it's only that part. So that means I'm going to redraw that curve so it's relevant to what we're interested in. So it's only this part of the curve. Just going to go over that in pink, which means that this part can go. So let's just relabel all that, because now we've got the real y equals f of x. So this is it. So it's only that portion that we're interested in. Now then, we're now in a position to read off what the range of this function is. And you'll be thinking, well, why do we need this? Because it's the inverse function that we're really interested in. Well, yes, that's true, but there's the range. Okay, now the range is going to go between 0, okay, because when you put negative 5 over 2 in, as we've got here, as you can see here, the y value is, of course, 0. All right. And the negative 5 over 2 is allowed. Okay. It's x is less than or equal to it, but 5 over 2, negative 5 over 2 is allowed. So the range is going to include 0. Okay. But as you'll notice, the y value has a limit. Okay. It cannot get to 2 or anywhere beyond that. So it is sandwiched between 0 and 2, but 2, it will never, ever get there. So there is our range. So I'm just going to make a note of that. So here we can have y is any real number such that y is between 0 and 2. Right, now that's what the sketch was for, to get that range. Now we're in a position to find the inverse function itself. So let's use the space over on the left. So how do we do this? Well, to find an inverse function, this is the process. So we'll go step by step. So step one. Okay, so write the function equal to y. So in other words, so write y equals 2x plus 5 over x subtract 3. Okay, write it in that way. So don't write it as f of x. Just simply write it as y, like you would do on a graph. Step two. Okay, this is for all inverse functions, so this is valid for anything that you try. Swap the variables. So swap x and y, and you don't have to do it in this order, but you don't have to do this as step two. You could do this at the end, but I like to do it straight away so I don't forget. Right, so we're going to swap the variables. So wherever we see an x here, that's going to become a y, and wherever you see a y, that's going to become an x. So we're going to rewrite the function now. So that's going to give us x is equal to 2y plus 5 over y subtract 3. So this is why it's symmetrical in the line y equals x, because of the swapping of the variables. The domains and ranges are going to swap over now. Okay, and the third step, which we're going to do now, which is the longest step. So step 3, we are going to make y the subject. Okay, now that we've swapped the variables. So your algebra skills are going to be tested here. So we're going to make y the subject, and this is the final step. So let's do that. So we've got our x as the subject. We've got to make y the subject. First of all, let's multiply both sides by y subtract 3. All right, so we've got x, and then we'll have y subtract 3, multiply both sides by y subtract 3. That will cancel the y subtract 3 on the right-hand side. It's equal to 2y plus 5. All right, let's expand. Okay, so multiply 3 by x, so we're going to get xy subtract 3x is equal to 2y plus 5. Okay, now we're going to collect all the y terms on one side. Now we've got everything, all the terms all broken apart. We need to get all the y stuff on one side. So I'm going to keep this term has got a y in. This term has got a y in. I'm going to nominate the left-hand side. So this side, I'm going to put all the y's on this side. So we need to subtract 2y from both sides now. So xy subtract 2y. And I can also add 3x to both sides. So that's going to be 3x plus 5. So I've now got all my y's on one side of that equation. You'll now see that I can now factorize out the y's. So I've got a y here as a factor and a y here. That's what I wanted. Let's factor that out. So we've got y multiplied by x subtract 2. Okay, is equal to 3x plus 5. And we're almost there. So this means that y is going to equal 3x plus 5 all over x subtract 2. And that is our inverse function. So we just need to write everything formally and we're done. So there's a lot of algebra work there. So I'm just going to draw a line there. So we write the function now. We don't write it as y. So therefore, f to the minus 1 of x is equal to 3x plus 5 over x subtract 2. And we now swap the domains and ranges for the original function. So what I mean is that this part here that we found earlier, that I've just highlighted in purple, that's now going to be my domain. But because it's a domain, I've now got to write all the y's in terms of x's, because we swap the x and y variables, don't we? We did that in step 2. Okay, so don't forget that because we swap the x and y's around here, we swap the x's and y's for the domain and range. So my domain is going to be x is any real number such that x will be sandwiched between 0 inclusive and 2 not inclusive. And the range, I don't have to do any work for that. I just reproduce the domain for my previous function, but I just swap the x's for y's. So my y values would be strictly less than or equal to -5 over 2. Okay, and if you plotted that, I can just show you briefly what that would look like. It's quite simple. You've got a really simple domain between 0 and 2 on the x-axis, so this would be for the inverse function. So it would go from there to about there. Okay, so that would be x equals 2. It's only defined for, so that's where the asymptote is, of course, and the y values, they go from -5 over 2 and down. So where would that be? Somewhere about here and then down. And then you would probably find with a slightly better sketch than what I've done, but they would be symmetrical about the line y equals x. Okay, so that concludes what's example 1. Okay, so our second and final example is a function g, okay, defined as x squared plus 1. And the first thing we have to do is state the range, then find the inverse, then sketch the function and its inverse on the same axes, and then some interpretation. Well, a good thing to do before we go A, B, C, D is maybe to just start with the sketch here. It'd be nice to see first of all, what the function looks like, and then it might help us in determining what the inverse function might be as well. Because if you're just asked to sketch in some instances, not in this instance, but in some, if you have to ask to sketch the inverse function, you might not know anything about it, but because you know it's symmetrical in the line y equals x, you can draw a really accurate sketch. So I want to see if the sketching and the algebra do in fact prove that this is the correct approach. So let's have a go at this sketch. Now, I'm going to sketch the function g first, and then I'm just going to use the symmetry of the line y equals x to draw it on. Now, let's just draw the axes first of all. And you'll notice that the domain is just for x values greater than or equal to 0. And it's a quadratic. It's a very simple quadratic with a vertical translation. So that should not be a problem to sketch this. We can do this directly. All right, so I'll sketch it here in this space. Okay, so there's the vertical axis, the y-axis, and the x-axis. And just label those. So that's going to be x, and that's going to be y. And remember, we're only interested in the positive x values, so it's just a positive quadrant. And x squared plus 1 is a quadratic. So it's going to have a y-intercept here at 1 and just the right half of the quadratic graph. Okay, maybe I'll just try that again. Something like that. No, I'm not happy with that either. There we go. That'll do. So this is y equals g of x. Okay, which is equal to x squared plus 1. And it's defined for all positive and 0, of course, x values. There we go. So it's just those x values. Now then, so that's the sketch. Now, if we were to draw the line y equals x, which is obviously the mirror line, I'm going to put that on. It's going to go diagonally. So if this is a 1-to-1 scale, it's going to look something like that, diagonal line. And we just label that. There we go. So it looks as though there is no point of intersection between my function g and the line y equals x. And we could test that if you're not sure by your sketch. This is just a little aside here. So if you're not sure, do x squared, or let's write it properly. Do y equals x squared plus 1 and y equals x intersect. Now, this could be a question from year 1, couldn't it? How would you determine that? Well, you would set up an equation. So you would have to solve this equation. X is equal to x squared plus 1. Okay, and then form a quadratic, so you would have x squared subtract x plus 1 equals 0. Now, does that equation have any real solutions? Well, how do you test that? You would look for the discriminant. So your discriminant, you've got a is equal to 1, you've got b is equal to -1, and you've got c is also equal to 1. Now, if you plug all that into the discriminant, you're going to have b squared, so that's -1 all squared. Okay, subtract 4 multiplied by a and c, which are both 1. So that's going to be 1 for the a and 1 for the c. Okay, you could also just plug this into your calculator and see what types of solutions you get. Now, I can see from this, so this is just going to be 1 subtract 4, which is -3. And you'll know, hopefully, from last year, that your discriminant is negative. There's no real solutions. So there's no real solution to this whatsoever. So we can state that. There are complex solutions, but not real solutions. So no real solutions. Okay, so the answer is an emphatic no. Okay, so it looks like my sketch is going to be pretty accurate here. Just a bit of an aside that we've just to check that if you're not sure. Now, we could also sketch g to the -1 on the same axes. Now, what I forgot to label was the y-intercept. The y-intercept is, of course, at 1. Now, if we do a mirror image of that in the line y equals x, the mirror image is going to appear on the x-axis also at the point 1. And my curve is going to do that. Okay, so that's going to be my inverse function. So this is y is equal to g to the -1 of x. Now, this is before I've even found out what it is. Okay, but I know my inverse function is going to look something like that using my sketch from the actual function itself. Okay, now we can do lots of things now. So going back to our question, we can see what the range of x is. Well, that's clear. Okay, the range of x, all the y values it can take. So let's just write those down. Okay, so range of g. Okay, really simple, all real numbers, but the y values are going to be greater than or equal to 1. Okay, so that's pretty straightforward. Now, the inverse function, we can go through our step-by-step process. We can find out exactly what this inverse function is that we've just sketched in green. Okay, so the first thing I'm going to do is write in the form that I stated in the previous example. So it's got to be y is equal to x squared plus 1. That's the first step. The second step is we are going to swap the variables. We're going to swap around the y and the x. So let's do that. Let's go back to the green. So this means that x is now going to equal y squared plus 1. And now we have to make y the subject. Okay, so first of all, I'm going to subtract 1 from both sides. We've just got one y term. So therefore, x subtract 1 is equal to y squared. And do we take the positive or the negative square root? Well, there should be a clue here. We've got lots of clues on display. You can tell by the graph I've sketched in green, the inverse function, that the range is obviously positive. Okay, it has to be because it's also the domain of my original function. All right, so it has to take positive values. Now, if I took the negative square root, that would give me all negative values. So that can't be the case. So we're going to take the positive root. So therefore, the square root of x subtract 1 is equal to y. And if you look at the inverse function I've sketched, it is a square root shape, square root graph, the root x translated to the right by 1. Exactly as we predicted. So let's write the inverse function. So f to the minus 1 of x is simply going to be, no, it's not f. Let's go. It's g, isn't it? Let's do this properly. Don't want it to be wrong. Okay, sorry about that. So g to the minus 1 of x is simply going to equal the square root of x subtract 1. And let's state the domain and range. Well, the domain is the range of the original function. Okay, the range of the original function is here. We found that in part A. There it is. So I just have to swap the variables. So we'll do that. So x is any real number. Just copying this down from part A. Any real number, but the restriction is that x has to be greater than or equal to 1. And for the range, we take the domain of our original function, which is up here. It's provided for us. There it is in the red box now. So we just write that as a y variable. So y, any real number, but the restriction being that y has to be greater than or equal to 0. Now, for the domain, you can also see this is true on the graph. You can see that because the square root graph, the positive square root graph has been translated to the right by 1, the x values begin from x equals 1 as we expect. So that seems to all tie in, as you can see here. All right, so that looks pretty good. So we've now got our inverse function. So that's really good. We've done the sketch for part C, so we've done that. So all that's left is to explain why the function and its inverse have no real solutions. Well, I mean, we could try and do this algebraically. It would be quite difficult, but we can see, just as a bonus question, if you like, we can see for part D, I'll just label the graph as part C up here. We can see from the diagram we've drawn that the graphs of g and g to the minus 1 do not intersect. Okay, so we can just state that. So y equals g of x and y equals g to the minus 1 of x have no points of intersection. So that means that they cannot ever be equal, which means that the equation would have no real solutions. Okay, so we've shown it graphically that this is the case. All right. Okay, so we've taken quite an in-depth look at inverse functions in these two examples. So please practice this, have a go at the exercises, and yes, so that concludes the lesson.